So thank you all for coming. Like welcome Dr. Gerber here. Come and talk to us about stellar evolution tonight. We continue lecture here at Purdue. He's done research at the Max Planck Institute for Astronomy, and this is his field of research. So he's going to tell us about it tonight, and we thank you very much.
So tonight I'll talk about low mass stellar evolution and non-canonical mixing on the red giant branch. Mouthful of the title, but hopefully we'll be able to sort of break that apart and see what it all means. And I'll mention a bit of research that I'm doing here, and I'll sort of plug some other areas of research. Mostly tonight I'm going to be talking about this one sort of mixing phenomenon that happens in stellar evolution, but as Amelia mentioned, I've researched basically all things stellar evolution or stellar abundances, ways to measure stellar abundances in stars. That's a lot of what I was doing before I came here at the Max Planck Institute for Astronomy. And so, that's what this is all going to be about. Let's just dive right in. So, stellar evolution and the stellar life cycle. So, some of you might have already heard about this, but basically what we've got is what's going to happen to a star as it sort of goes through its life cycle is largely dependent on the mass of that star, because that's going to tell us how much energy that star generates. That's going to tell us what kind of processes can happen, the physics going on inside that star. So a star is going to start out, some sort of molecular gas cloud is going to collapse in on itself due to gravitational collapse. So we don't really know exactly what starts that process yet, and there's a lot of theory between how we go from this molecular cloud over here to a star, but the basic is that something comes along, probably some pressure or something like that, that knocks some sort of large nebula into this situation where gravity can take over, pull it all together, and that gravitational collapse is going to occur until something fights back. And that thing that fights back is basically we collapse all the material in far enough for fusion to kick off. And when fusion kicks off, we get this pressure from the inside of the star, and we're able to get stability again, basically pressure versus gravity. And so for massive stars, things with more than 8 solar masses, they're going to basically burn through, they're going to fuse hydrogen into helium, helium into carbon, so on and so forth, until they get to iron. Once they get to iron, they can't fuse anymore. It doesn't make energy sense to do so. But you actually lose energy in fusion rather than gaining energy. And so those stars then collapse in on themselves, and that's when we get these big old explosions with supernova that lead to these compact objects like black holes and neutron stars. What we're talking about today are low mass stars. And when I say low mass, in this case, we're talking about anything, certainly these stars are less massive, they're not going to go supernova, so none of these stars are going to have these exciting endings where they sort of go through these large explosions. And we're talking even less massive than this sort of divided 8 solar mass. Today I'm going to be talking about a phenomenon that occurs mostly in stars that are masses right around the mass of our sun. So maybe half the solar mass to about 2 solar masses, so stars right in there, and what they're going to do. So those stars are going to do something similar here. They're going to burn hydrogen in their core until they run out there. It's going to turn into helium. They're going to go through this red giant phase, and then towards the end of their life, they're not going to have enough mass to cause this big explosion to burn heavier elements. What's going to happen instead is as they hit these later stages of helium burning, there's not enough mass to hold the material together. Their outer layers start blowing apart, and that leads to these planetary nebulas with these white dwarfs, which are basically the cores that are left over, sitting there sort of inertly that slowly cool over time. So we're talking about everything down here, these low mass stars, and the kind of evolution processes they're going to go over. And so I wanted to review, because I wasn't sure how many had astronomy backgrounds here, because some sort of background in the Hertzsprung-Russell diagram real quick before we keep talking about stellar evolution, because this is a tool where we're plotting luminosity versus temperature on the x-axis. Notice here, hotter stuff is over here, cooler stars are over there, brighter stuff is at the top, fainter stuff is down here at the bottom. So this is a diagram called the Hertzsprung-Russell diagram. If you're not familiar with it, just be patient, bear with me for a minute. And it's something that's really useful when we talk about stellar evolution, because it's important to see what's going on with these stars, and it's really easy to see the phases as they go through on something like this diagram. So this is a plot from a catalog, the Hipparcos catalog, basically a lot of bright nearby stars. are being plotted here, and you see they all sort of fall along what we call this main sequence of stars, where these are all stars that are burning hydrogen in their cores. If I'm more massive, I'm going to have a hotter surface temperature. I'm going to be more massive, I'm going to have a brighter luminosity as a result. Right? Luminosity is going to go as temperature to the fourth, but it also is going to go as radius squared. So in fact, I can have cooler stars. Here on the main sequence, those stars, their radius is going to shrink, they're going to be cooler, their luminosities are going to be lower. A star like our sun is going to be sitting right around here. But eventually those stars, things can happen in their evolution that causes their radius to increase. And as that radius increases, even though those stars are cool, their luminosities are going to increase. Flux that we observe can also go as that radius squared. So those two sort of fight. And we can watch the stars move around in this diagram as a result of inner processes that are taking place. And so oftentimes for the physical measurements, we're talking about luminosity and temperature, but often you might see this instead of a Hertzsprung-Russell diagram as a color magnitude diagram. And all that is instead of temperature, we're looking at color, the difference between two filters we observe through a telescope, but that relates pretty well to temperature. And we look at the absolute magnitude. So if you're not familiar with the magnitude system in astronomy, it's basically a logarithmic system for measuring the flux from a star that we see in the telescope. So we've got logs here, and for a fun sort of historic reason, basically, that we've stuck with forever, as most things in astronomy that don't make any sense anymore, as we decrease in magnitude, we increase in luminosity. So over here, you'll notice those are flipped. We've got larger magnitudes down here for fainter objects, and lower magnitudes all the way up to the negative numbers for brighter objects. And that goes way back to the Greeks. This is for why that happens, but we've stuck with it. I don't know why. So anyway, this is our Hertzsprung-Russell diagram. If we look at a star, a low mass star like our sun, we've got something here called the 0H main sequence. So these are where stars are going to sit when they start off. They first form from that nebula, they form down to a star, they start burning hydrogen in their cores. A star like our sun is going to do that for roughly 9 billion years. So we're about 5 billion years in, we've got about 4 or 5 more to go. And it's going to keep chugging along, burning hydrogen in the core, until eventually it's going to run out of hydrogen in that core, and it's going to have converted everything from hydrogen into helium. So now we've got a problem. Gravitational collapse is going to take over again. And it's going to shrink down that core, and it's going to keep collapsing things together until eventually we kick on hydrogen burning in a shell around that core. Basically, the outer layers have become hot enough that we can now burn hydrogen in a shell around the interior core. And what that does, that hydrogen burning is actually now much hotter. We've had some gravitational collapse. We've got higher pressures and temperatures as a result. And so the outer radius of the star expands. And so we get this red giant phase that kicks off. So now we no longer have hydrogen burning in the core. We're burning hydrogen in a shell around a helium core there. And that star is going to do that. A star like our sun is going to keep doing that for about 1 billion years. So we sort of lose the order of magnitude every time we go to a new phase on this diagram here. And as it continues to burn hydrogen, its exterior radius is going to keep increasing and increasing. And this is going to happen and continue to happen until this unique principle happens up here, where we get core helium ignition. And basically what happens is the sun goes out, and buys some sunglasses and a convertible, and it goes through its midlife crisis right here, and it starts the process all over again. It dips down, and now instead of hydrogen burning in the core, we've got helium burning in our core. So we've got helium burning. The sun's going to contract a little bit. The radius is going to decrease, so the luminosity is going to decrease. We're going to drop down here, start burning helium in the core, and then the same thing's going to happen all over again. The sun's going to start increasing in radius slowly until it runs out of helium in that core. It's going to start burning helium in a shell around it. That kicks off this asymptotic giant branch phase, because it happens sort of here. I've zoomed in everything on this diagram that I found. But if we look at this in the color magnitude diagram, as I'll show maybe a bit later, we can see it. These two phases, this asymptotic giant branch and this red giant branch phase, happen right next to one another. And we again got this increase in radius, this increase in luminosity. That core helium burning is going to happen a lot faster. It's going to happen at a much higher rate. It's only going to last about 100 million years until eventually we start this helium shell burning. So the same sort of thing takes over. We're burning helium in a shell, just like we were burning hydrogen in a shell. Now we've got helium then a hydrogen burning shell, an inert core full of carbon, as we converted helium into carbon. That's going to last less than 1 million years. And as our sun, a star like our sun is doing that, it's blowing off material, continually ejecting material. And so eventually all of that's going to end as it kicks off material and turns into this planetary nebula, which is not how planets are formed. It's a misnomer from a long time ago when these nebulae were first observed, and it was theorized maybe planets formed out of there. They called them planetary nebula, and the name stuck. And so then eventually everything's going to be kicked off the way. We don't have enough mass to burn that carbon in a star like our sun, so it's going to dip way down here. We sort of saw these in the last diagram and turn into one of these white dwarfs, where basically what I've got left, I've kicked off all of the outer layers, and in the center I've got a very carbon dense core. The only thing keeping it from collapsing is the fact that electrons can only get so close to one another. There's an electron degeneracy pressure, basically, where I can't get past that Coulomb force from electrons. I don't have enough mass to do that. And so I'm left with this core that just burns really bright, but it's really small. A star like our sun, that core will be roughly the size of the Earth. And it's going to sit there and slowly cool over time. It's going to slowly get cooler and cooler because it's not burning anything until eventually it sort of dies out and becomes completely black. So that's sort of all of our phases of evolution as we go through. We've got a lot of them taking place. And the main one I'm going to look at as we talk about mixing is going to be this one right here. So I focus a lot on what happens in this red giant phase of stellar evolution for stars like our sun. So what are they going to do once they hit this red giant phase? We've got a lot of things going on inside the star. So let's take a look. If I look at a star like our sun, and I took a slice out of it and sort of looked in the center, what I would see is I'd have this photosphere around it in a lot of different places. We've got flares coming off. We're ejecting material from this convective zone. So we've got this convective zone on the outside where heat is being transferred through convection, just like boiling water. And so we've got this bubbling of material here on the outside layers. Inside of that, I've got a radiative zone. Heat is being transferred through radiative transfer. We're basically just atoms bumping into each other. And deep inside the center, I've got that core where hydrogen is being fused into helium over time. All right. So we've got this taking place in our sun right now. This is what it would look like if I took a look on the inside. And over time, eventually, we're going to run out of hydrogen. When that happens, we're going to be left with this helium core in the center. So a very fancy graphic, but it gets the job done. So nothing's really to scale here. We've got a star like our sun cut apart. We've got our convective zone, our radiative zone, and eventually we get to a point, we burned all that hydrogen. Now we're left with this helium core. So there's no more pressure support. So that helium core is going to contract a bit as gravity pulls it in. As it does so, it's going to ignite a hydrogen burning layer around it. This hydrogen burning is hotter than that core hydrogen burning. So what it's going to do is push away the outer edge of the radius, and it's going to keep doing that and go further and cause this massive expansion of a star like our sun. And so just to sort of see what this looks like, here is our sun as a red giant. Its diameter is roughly going to be 2 astronomical units, an astronomical unit being the distance from the Earth to the sun. So the Earth is going to be sitting sort of right on the edge of what our sun will look like when it becomes a red giant. Some people say it'll be inside, some people say it'll be just outside, but it's going to be right around there with a radius of 1 AU. We're going to be right on the edge of the sun. And what the sun looks like now is this little yellow dot down here. You can see it zoomed in. It's got a diameter of 0.01 AU. So we're going to have 100 times increase in the radius of these stars as they change from the main sequence to the red giant branch. So now I mentioned I want to study red giant branch stars. I want to study stars like our sun in this red giant branch phase. So how exactly can I do that? Well, one thing to do would be to sit and wait around for our sun to turn into a red giant, but we've got an awfully long time to go. We've got about 5 billion years, and I don't think I'm going to make it, as hopeful as I may be and put my life there. So instead, what we do is we look for stars that were born earlier than our sun and have already transitioned into this red giant phase. And one place where a lot of these stars exist are in these things called globular clusters. And so globular clusters are exactly what their name suggests. They're clusters of stars, millions of stars worth, that were formed right at the same time as our galaxy, right at the beginning of the universe. So about 12 to 14 billion years ago, these objects first formed. So I've got stars that have already gone through that 10 billion years roughly of that main sequence phase and are red giants. And I've got millions of them, right? I've got a whole bunch of them. And they're named globular because we've got so many stars, the cluster shaped gravity is going to pull it into a nice sphere for us. So we've got a nice globular shape. So traditionally, these have been thought of as simple single stellar populations. I have a population of stars. They had a bunch of material a long time ago. All of these stars formed. And so we've got these oldest datable objects in the universe, 12 to 14 years ago or billion years ago on average. Traditionally, they're these non-rotating sort of lumps just sitting around. Their typical masses, again, we have hundreds of thousands to millions of stars, so the solar mass matches that. There's about 150 of them floating around in the Milky Way that we can go observe. So these are nice, bright, red giant branch objects sitting in the Milky Way. And what's nice is that the Milky Way, if I look at our galaxy as it's plotted, and what I've plotted here is data from the Gaia mission, which is just looking at a lot of stars in our galaxy. And so in the disk of our galaxy is actually a bunch of dust and stuff that's difficult to observe. Well, luckily for us, if we want to study these red giant branch stars and globular clusters, they're going to sit out here instead of in the disk, in the halo. So they sit in this observable galactic halo. Here are all of them. They're all these blue lines, and it's traced their orbits going around. We've got basically 150 of them, and we can go out and observe these objects to look at stellar evolution. Specifically, if we're looking at globular clusters, while we can trace, they can be used sometimes to trace the oldest objects. Since they're the oldest objects in the galaxy, they've been used to trace the galaxy formation history, but they're also used as these stellar laboratories to study evolution of these old, specifically low mass stars. Those higher mass stars are going to evolve quickly. I haven't mentioned that before. Those high mass stars, you can kind of think of them like bugs in comparison. They sort of are born quick, they die quick, they churn through all of their mass and they blow up. So if I want to study these older, low mass stars that take billions of years, I need these kind of objects to do so. Where we can look at our stellar evolution of these guys down here, and we can use these as laboratories to study what's happening. I can look at any chemicals, and if I can measure the surface abundances of different elements of these stars, they can tell me what's going on inside the star, what's causing it to change, if I see any changes take place, et cetera, as I look at stars at different age in these different clusters. So what we're going to be talking about is these globular clusters and red giant branch stars within them to see if they can answer some questions about what's happened to these stars as they go through this red giant branch phase. So here's a globular cluster. A different view of it, instead of a nice pretty picture, what we've got is our color magnitude diagram again, where I've got luminosity, so bright objects up here, and I've got warmer objects over here, fainter objects over there. Notice our main sequence isn't quite complete, right? Because all of those younger, those high mass stars died off a long time ago. They're already dead. What I've got are low mass stars that haven't evolved off the main sequence yet, and then I've got this turn off, where I've got stars that are starting to turn over at these masses. And at slightly higher masses, these stars have already started going up the red giant branch. You can kind of see then they come back down and fall here where we've got helium core burning. That's called the horizontal giant branch. For some clusters, it looks vertical. I don't have time to talk about that, unfortunately. And then they go back through this asymptotic giant branch phase where you can see there it lines up right next to that red giant. And so this is M13. It's named for the Messier catalog of objects. Messier went around and measured a bunch of bright stuff that wasn't stars and just cataloged it. There's over 100 of them. This one is M13. It's a really popular cluster to look at. It's bright. It's relatively close and sort of has this simple stellar population that lines up with just what we expect. So good. We've got a single population. In metallicity, at least, because if I had different metallicities, stars would be different temperatures, and they'd be jumping all over the place in this diagram. So I can look at these objects and study these red giant branch stars and see what's changed between these main sequence branch stars and these red giant branch. And so everyone thought we had a simple stellar population. What I'm going to go do is I'm going to measure some abundances of these stars, and I'll figure out what carbon abundances look like in red giant branch stars. And immediately they started running into issues. So notice the year back here was 1981. So over 40 years ago, we looked at the carbon abundance of these stars. And the way we did that is we took something called a spectrograph. We looked at lines in the spectra of a star. We can basically break apart the light from that star as it comes through. Our spectrograph is going to separate that into wavelengths. Carbon atoms are going to cause a different sort of absorption features to be seen in these wavelengths. And from how deep those absorption features are, I can then measure carbon abundance. That carbon abundance here is written as this ratio, carbon over iron. So that's the ratio of carbon to the iron abundance in the star. And these brackets just mean that it is a log of that ratio compared to solar, whereas the solar carbon per iron ratio is going to be 0. And then we bracketed that off, so we're going to go from there and take that to be our 0 point, log 0 point, any difference. So for example, if I have one difference, I've decreased this ratio by an order of magnitude of 10. Right? So this is sort of a weird plot to look at this. I'll show some easier ones to look at. But Sunsit in this paper went through M13, that cluster I just showed, measured a bunch of carbon abundances along this red giant branch, and what he found was interesting. Basically here he's color coordinated points based on the carbon abundance he found in their surfaces. And what he found was that stars down here at the lower end of the red giant branch, they're colored in darker. They have higher carbon abundances than the stars up here at the tip of the red giant branch. So already we've got a problem. If I've got a nice simple stellar population, and I've got this situation where the surface abundances of my star shouldn't really be changing along this red giant branch. There's nothing that would allow that to happen. And yet what I see is a change in carbon abundance. So is this something weird that was just happening with one cluster? The answer is no. This was observed all over the place in all kinds of clusters. You saw that over here on the y-axis, we've just got carbon abundance, and we're plotting that versus luminosity. So as we go up that red giant branch, the carbon abundance fell for basically every cluster that went and measured carbon abundance. So we've got something weird that's taking place. We've got carbon depletion happening on the red giant branch. So this is weird for a couple of reasons. We expect a little bit of carbon depletion when a star first kicks off this main sequence into the red giant branch. And we expect a little bit to occur as we go right through that first curve in this subgiant sort of class, because as we had before, remember we had this main sequence star, that helium core collapsed, we had a hydrogen burning layer, and the radius started to increase. What also happens here is the convective zone at the same time starts plummeting and decreasing in. And as that convective zone decreases inwards into the center of the star, it's going to interact with some material that's already sort of been processed by the center. And that material is going to be slightly depleted in carbon compared to what was already at the surface. We've got a convective zone that's churning material, and so it's going to bring material from the center up to the surface. And so we expect an initial quick drop, but over time, this hydrogen burning layer pushes that convective envelope zone back out. And so after we've gone through this subgiant phase and are securely on the red giant branch, we don't expect any more mixing to take place. We don't expect any material to escape from this hydrogen burning layer, and this convective zone is no longer going deeper into the star. It's going the other way. So we shouldn't be able to bring any fresh material to the surface. The carbon abundance should be locked in pretty tight, and yet we see a depletion in carbon. While we measured a depletion in carbon, we measured at the same time an increase in nitrogen. So there was this anti-correlation measured in globular clusters, where stars with lower carbon had an increased nitrogen value. So we've got a nitrogen value measured here on the y-axis, carbon here on the x, and we see this sort of anti-correlation all the way back to 1984 when we first looked at clusters. We already have this problem. So we've got decreasing carbon, we've got increasing nitrogen. And so we need to come up with an explanation for this. While we have decreasing carbon and increasing nitrogen, we also found the same sort of anti-correlation with oxygen and nitrogen. So we also had where there was less oxygen, there was an increase in nitrogen. And we saw something else that was interesting. We can actually measure the types of carbon that are found, carbon 12 or carbon 13 on the surface. And when that happened, what we saw for stars when we measured the ratio of carbon 12 to carbon 13 we've got that a value around 4. But canonically, we expected that value to be 20 to 40. So based on stellar evolution models at the time, we expected there to be a ratio here of 20 to 40. Instead, it's roughly 4. And the big change that's going to happen there is we're going to have this large increase in carbon-13. So all of this is pointing to some sort of material coming from the surface, which I'll call deep mixing, and we'll talk about a little bit more. And this material that's coming up to the surface, some of you might know, some maybe have figured it out, is CNO cycle material. So the CNO cycle is this cycle that happens deep within a star, and it's basically a way that hydrogen can be burned or fused into helium. So there are a couple of different ways that hydrogen fusion can happen. One of them is the proton-proton chain, right? And so the proton-proton chain is sort of the simplest way that you can think about for hydrogen to turn into helium. Basically, I take two hydrogens and I mash them together. And what we get out of that result is we get a heavy hydrogen, so a hydrogen with a neutron sticking with it. So we've got a proton and a neutron now. I stick another hydrogen into that, and I get helium-3. So not quite there to helium yet. If I do that process again and combine two helium-3s, well, what's going to come out on the other side, I'm going to have two hydrogen atoms left over, and I'm going to have a fresh helium-4. Okay. So you see through this proton-proton chain process, 4 hydrogen atoms went in, 2 hydrogen atoms come out with a helium atom. So I've converted 2 hydrogens into 1 helium. That's one way that we can turn and fuse hydrogen into helium. The other way is through this thing called the CNO cycle. So the CNO cycle is doing the same sort of thing. I've got a proton or a hydrogen atom that I want to turn into a helium atom. But instead of doing it by just sort of mashing 2 hydrogens together, we're going to use carbon as a catalyst. That's one way to think about this. And so we're going to take a carbon-12 atom and we're going to add a proton. And what's going to happen is it's going to turn into nitrogen-13. That nitrogen-13 isn't very stable. It doesn't like being nitrogen-13. So it's going to beta. It's going to throw off an electron and go back down into carbon-13. Carbon-13 then is going to get stuck with another proton. Another hydrogen atom is going to come along and stick to carbon-13 and give us nitrogen-14, which is nice and stable. So notice this is sort of the big holdup in this CNO cycle. Nitrogen-14 likes being nitrogen-14. So it takes a lot of work, but eventually we're going to come along and hit it with another hydrogen atom and turn it into oxygen-15. That's going to beta decay. Oxygen-15 is very stable. It's going to turn into nitrogen-15. We hit that with another hydrogen atom. And what happens is it's going to turn into carbon-12 again and spit out a helium atom as a result. Okay. So what we're left with after this whole thing goes around is I've got my carbon-12 atom back out, and I've turned this hydrogen, I've turned a couple hydrogen atoms into a helium one. Go along the way. Hydrogen down to helium. This is just another cycle that can go on in super hot stars. This is the main one that we're talking about and focusing on, because you'll notice that what we're doing through this cycle as it's taking place is, one, I've got carbon-12, I'm making carbon-13. So if I wanted extra carbon-13 material, this cycle would create it. I'm also making a lot of nitrogen. I'm converting carbon into nitrogen as this goes through. And a lot of nitrogen is going to be sitting there waiting, because nitrogen is super stable. It's going to take a long time before it gets converted. So if I dredge this material as it goes through, as I've got some sort of CNO cycle taking place, then I'm going to get a decrease in carbon, because the material inside compared to outside, I've converted that carbon into carbon-13 and nitrogen, which then matches the other increases that we saw in these red giant branch stars. So basically, all of this material that we're seeing is showing us that the CNO cycle material is being drawn to the surface, because what matters, sort of what decides which process we use for burning, whether we're doing the proton-proton chain or the CNO cycle, that's going to depend on the temperature that the burning is taking place. So whenever I'm fusing hydrogen into helium, I want my energy rate to be as efficient as possible. For the proton-proton chain, that curve looks something like this. And so for something like the sun, when we're core burning hydrogen, it's mostly proton-proton changing. But then when we start doing hydrogen burning in that envelope, it's at a much warmer temperature. So we've increased that temperature to the point where I'm somewhere over here. And so the more efficient cycle is going to be the CNO cycle, not the proton-proton chain. So that hydrogen burning envelope is going through this CNO cycle. It's going to have this CNO material that can then be brought up to the surface. And as a result, we get abundance patterns that look like this. So this is a bit of a newer work that was done in a globular cluster M10. There's a couple different color coding things going on here that I don't have time to talk about. The focus here instead is just to notice that I've got carbon, I've got stars that were sitting down lower on the red giant branch, then they hit this certain point, which I'll talk about in a minute, in magnitude, and that carbon decreased, and that nitrogen started increasing in all of these stars. So this is a lot more stars we were able to observe with our newer telescopes. We were able to get a lot more data, and watch as this decrease happened all the way up the red giant branch to the very tip, and we had this increase in nitrogen take place. So the CNO cycle material that's burning in this hydrogen shell is being brought up to the surface and causing these decreases, and it looks like it kicks off at this point on the red giant branch. Now, this point on the red giant branch is something called the luminosity function bump. And what it's a result of is a few things. If we look at, again, our model of our star that's going through this evolutionary process, and now we look at, in addition, we've got this sort of window that's showing us what's taking place with this star as it evolves. It's going to start as this main sequence one. As we've already said, that core shrinks down. We come up to this subgiant phase here. We start this hydrogen burning layer. CNO cycle burning material is starting to take place. That convective zone dips in, the outer radius starts increasing, and we're off to the races on our red giant branch here. Now, eventually this sort of all balances out. And when it does, what I'm left with is this barrier called a chemical weight barrier, mu, which is basically the difference between, I've got this fresh hydrogen material that has a certain chemical weight. Inside, I've got different material that has already gone through some sort of process that has a different chemical weight. And so in general, material can't cross this because we have this barrier between the two. And so that convective envelope is going to get pushed back out, but that mu barrier, this chemical weight barrier, is going to get left behind. Then this hydrogen burning layer basically goes off and starts looking, as it burns material, it burns up all this fresh hydrogen, it starts looking for more fresh hydrogen. So it starts expanding out as its temperature increases. And eventually it's going to run into this mu barrier, and there's going to be this influx from that chemical weight material, this fresh hydrogen material that's going to allow it to burn brighter and burn even hotter than it was before. And so as a result, the star is going to sort of stutter and go back down the red giant branch, and it's just going to sit here while the hydrogen burning layer doesn't keep expanding. And then eventually it's going to burn through all that fresh influx of material, and then it's going to go back up the red giant branch. So we've got sort of this period where stars are coming up. Some stars are on their first way going back up. Some stars are coming back down. Other stars are still going back up. And either way, what I need to do is come across this mu barrier if I want anything to get from this hydrogen burning layer out into this convective envelope. And so stars, once they've gone past this point, that's when they start mixing. And it looks like this bump in the luminosity function. So we have the number of stars at a given luminosity. We get a pileup here. And that pileup is because some stars are coming up, other stars are going down, and other stars are going up for the second time. So we sort of end up with this pileup of stars that are all going through this process. Their internal cores, this hydrogen burning layer, has hit this new material, and it's caused them to sort of go through this stutter until they burn through it and start expanding again. And once they do that, their envelope has now gone through that mu barrier, this chemical weight barrier. And so now if there was any process that we haven't explained yet that could cause material to cross, it would happen. And so this is the luminosity function bump here. You can kind of see it a little bit better here. You see this pile up right there on the red giant branch in M10 and M13. It's that color magnitude again. You can see it better on some clusters than others. And we can observe this luminosity function bump and measure where it happens for a given cluster and its given sort of metallicity. How many metals or elements other than hydrogen and helium a star has is going to govern where this luminosity function moment takes place. So it's been measured for a lot of different clusters. We've seen this sort of pile up take place. So it's something pretty well known. Now, we've got this mixing. It's going to take place after we hit this luminosity function bump. Basically, what we've got is something that's non-canonically described that is causing material, even though it's sort of allowed to cross because we're past the chemical weight barrier, past that. But normally, material is able to sort of be segmented, stay separate from this burning layer and from the convective envelope. Is the traditional canonical sense, so nothing would cross. But something else is happening. We've got this non-canonical mixing. There's a few different ways that experiment that sort of describe what's happening. One way that this paper looked at is called thermohaline mixing, which is basically what it thinks is happening is it's named after a similar process that happens whenever you have salt water meet fresh water. And basically you have these saltwater fingers that sort of break through the fresh water. And so an idea is something similar is happening here, where that hydrogen burning envelope has sort of fingers of material that sort of break through at certain points where the pressures and the conditions are just right. And once they break through, the convective envelope can then take that material and sweep it up to the surface. So we end up with these depletion zones. Now, the problem is that there isn't a theory that fully matches observations yet of this process. It's something we've observed for a long time, and we still don't quite have a full explanation for it. So what my research is doing is looking to do something similar to what this paper did. This paper went through of a cluster. This is NGC 6397, a big phone number from the catalog that this cluster was observed in. And basically what they found is a couple of elements that should change as a result. So one is carbon. We've mentioned already that that's going to decrease due to this mixing. The other one that they looked at was lithium, which we haven't mentioned yet. But lithium basically is this really fragile element. And so lithium it has existed. It's part of Big Bang nuclear synthesis. So since the start of the universe, stars have had lithium. It's been around, it's been there. But whenever lithium gets involved with any amount of heat, it's almost immediately destroyed. So if I was looking at, say, material that was coming from a hydrogen burning layer, it wouldn't have any lithium. It'd have a lot less than, say, the surface of the star, because it's already been destroyed. So that means lithium is also going to decrease as a function of brightness for the same sort of reasons as all the others, bringing burning material that's gone through burning up to the surface. And so what they did here, they basically got this model that constrains thermohaline mixing. They do it through this sort of, basically it's just a set constant for how much mixing has taken place. And what they found is that if you apply the sort of what had already been done in the literature, they found that basically you needed different values of that constant to match different elements in the same cluster. So these stars had the same mixing take place, but to match it, I needed different values of the constant. And so they had to sort of rectify this by changing the theory, and they came up with this solution here that again doesn't match it exactly, but it comes much closer. And so our observations are looking to do something similar. Basically, what I want to do is look at these clusters that we've measured a ton of different stars. For example, M10, we've got a bunch of carbon and nitrogen. And then I want to add all of the elements that are going to be affected by this mixing. So we went through, and the next step we did is we looked at the carbon isotope ratio. And so we measured carbon isotope ratio for a bunch of stars. We got that value there. It is right between 4 and 7, just like I said, is what we observed. Much lower than expected canonically. So we did this for a bunch of different stars in M10. And then what we did is we did the same sort of thing where we compared canonical, or not canonical, but these thermohaline mixing models in the literature to see if we could find something that would match the carbon isotope ratio and the carbon and nitrogen abundances for the cluster. Spoiler alert, we didn't. So as you can see, we needed a much larger coefficient of mixing to match our carbon isotope ratio than we did to match the carbon and nitrogen abundances for the same cluster. Okay. And so the next step of this research is we're going to add lithium. So we've already got measurements. We've already got sort of the spectra that we need to measure lithium for these stars. I'm working right now with an undergraduate, Maya Talbert, who's doing awesome stuff. She started working with me this semester to measure lithium in these same stars of M10 from data that we took back in 2016. Once we have that, we'll have this sort of full suite of carbon, nitrogen, carbon isotope ratio, and lithium abundances. Then we can go in, constrain models for the mixing, test models like the one I showed before, see how well it works, how well it fits stars in this cluster, which is going to be different from the one they used. Maybe that can rectify some of what we saw. Does it also make lithium and carbon match up? But does it also match the carbon isotope ratio? Because whatever model we have for this mixing is going to have to match all four. And then so future work, we've got similar data for other clusters. And the idea will be to go and continue adding clusters because this mixing rate is dependent on a few things. One of those things is the metallicity of a star, or what stuff it has other than hydrogen and helium. And we expect basically for stars with lower metallicities to have higher rates of mixing because they should have larger and more active convective envelopes as a result. Because what I get with metals is I get more cooling in the star's outer layers. So we should get higher rates of mixing, but we want to put that to the test. So we go look at other clusters that have different metallicity values of those stars, and we keep applying the same model, and we keep constraining it until hopefully we can come up with a model that finally sort of fits this non-canonical deep mixing period that happens when the stars on the red giant. So that's all I have to talk about. I'll just put this up here, sort of my advertisement. If you're interested in any of this research, I'm looking for undergraduate researchers to come and help me. Feel free to send me an email. This is one area we're looking at, but I've also got ideas for other projects, one such being N4 activity, if you're interested in any of that. If you're also interested in looking at large data sets, I'm a member of a couple of different big surveys that are going to go out. One of them is Foremost, one of them is Plato. If you've heard of either of those, Plato is basically going to go out and try to do what the Kepler mission did, and it's sort of a different fashion. So the Kepler mission looked at, I'm way off topic now, I'm sorry about that. The Kepler mission sort of looked at one area of sky and tried to find as many exoplanets in that area as it could. Plato is going to do the opposite and look at a bunch of stars all over the sky and try to find as many exoplanets in nearby stars as it can, stars that we could maybe observe. And so we're going to have a lot of data on a lot of different nearby stars. I think it's planning on hitting 1 million stars a night. Foremost is something that's going to look at spectroscopy. It's going to do spectroscopy of the entire galaxy, basically, with a 4-meter telescope, hoping to look at, again, roughly around 1 million different stars a night. So I'm a member of both of those collaborations. So I've got access to a large amount of data sets and need help to analyze it, basically. So if you're interested in any of that, let me know. And also in astronomy software development. So I've developed this software that basically goes through and models what stellar spectra is supposed to look like, and it's used to determine abundances and things like that. And we're actively developing that and looking for students to help. And as always, too, I'm happy to discuss any projects, ideas that you might have that relate to anything sort of blanket stellar abundances and evolution that we can talk about maybe figuring out a project. So that's all I've got. Questions?